Welcome to another edition of Coonrod's Corner, brought to you by the Rogers Corporation. Today's topic, material properties which are critical for PCB thermal management and thermal stability. Now here's your host, John Coonrod.
Hello, my name is John Coonrod with Rogers Corporation. I am a technical marketing manager. Today I'm going to be talking to you about reliability and also RF stability for printed circuit boards considering thermal effects. And to begin with, I'll talk about heat flow and thermal effects, and then finally I'll talk about other aspects that can impact RF stability and reliability for that matter. Now this is a really large topic, and I'm just going to be hitting the highlights here. And for the viewer, I'd like you to go to our Rogers Technology Support Hub, and there you can get much more information on this topic. At the end of this video, you will get a URL for the website. Shown here to the left is a very simple model right out of Physics 101 text, and what it's showing is the relationship of heat flow, and the formula there, heat flow is H, and for thermal management you want heat flow to be increased, and H is equal to K, which is thermal conductivity, A is the area between the hot and the cold reservoirs and how they connect to the thermal connector itself, or conductor. And then the delta T is the difference in temperature between the hot and cold reservoir, and then the L is the distance between them. Now that's the standard heat flow model, you might say, and then on the right is how you apply that to the printed circuit board industry. Here I'm showing a cross-sectional view of a microstrip circuit where the signal's on top and ground plane is in the middle, but basically the bottom of the circuit, and the ground plane is adhered to a heat sink. So the ground plane and the heat sink are at the same thermal potential, and what you want to do is have the heat go from the signal plane, where we're assuming the heat originates, and go through the material, so the material's acting as the thermal conductor, to the ground plane, and then the ground plane will be the same thermal potential as the heat sink, and that's how you get the hot temperature from the signal plane to the colder temperature of the heat sink and keep your circuit cooler. Shown here is bulleted information on many topics related to thermal management, and many times I'll have someone ask me, what is the maximum power that you can apply to a circuit? And it really comes down to, you can apply as much power as you want to the circuit as long as you do not cause the circuit to violate the MOT. MOT is the UL rating of maximum operating temperature, and as long as you do not violate that, then the circuit should perform as expected for an indefinite period of time. So minimizing the circuit temperature is obviously good for many things, but also you need to make sure you understand the MOT of the circuit and that the circuit is not heating beyond that. And one way to do that is reducing the insertion loss, because in a reduction of insertion loss is a reduction in heat generated. And if your circuit is using a thin substrate, then using a smoother copper can help to reduce the insertion loss. If the circuit's using a thick substrate, then you may want to look at a different material with a lower dissipation factor. And then also an increase in thermal conductivity, which is K in the formula, that has a direct impact on heat flow. So increase in thermal conductivity means increase in heat flow, and that means the circuit remains cooler. And I do have some examples here off to the right that show some of the thermal conductivity of different materials used in the industry. Now I have FR4 in there, even though that is not an RF material. Many times with hybrid multi-layer PCBs, the heat flow path is going through the FR4, so that's why I've included that in the materials here. Now also another thing you can do is use a thinner substrate, and according to the formula, L, that's the thickness, if that is thinner, then that is going to cause a shorter heat flow path and also improved heat flow, increased heat flow, and again that's going to decrease the circuit temperature. That's a good thing. However, when you have a thinner substrate, normally the insertion loss is increased, so you need to consider the difference of insertion loss if you go that route. And then last, one thing that's usually not thought about much for thermal management is dielectric constant, and if you use a lower dielectric constant material, that's going to allow you to get a wider conductor, and the wider conductor means the area that's part of the formula A, that area is going to increase, and with an increased area you have increased heat flow, and that's good for a cooler circuit. The other thing with having a wider conductor is you have less conductor losses and also less insertion loss. With less insertion loss, you have less heat generated. So all around, that's a good way to go as well. Minimizing the temperature of the circuit is important for reliability and also for RF stability. However, there are several other topics that need to be considered for RF stability and actually reliability. One of them is TCDk, thermal coefficient of dielectric constant, and I'll explain that a little more as we go along. Then moisture absorption can be another concern. Short-term high temperature exposure such as soldering or assembly or rework. That's generally not an issue, but there are some exceptions there. And then finally, long-term thermal aging. I'll also give some information on that as well. Shown here is some information on testing circuits for TCDk. TCDk is thermal coefficient of dielectric constant, and that's how much the dielectric constant will change with a change in temperature. And all materials have this property. Now, our materials are formulated to have a very minimal amount of TCDk, so the dk does not change with a change in temperature. But that's not true with all the materials in the industry. What I'm showing here is dk versus frequency curves. Y-axis is the extracted dielectric constant. X-axis is frequency from 1 to 100 gigahertz. And there's actually 3 different curves that are being shown for each one of the circuits tested here. And the first curve is the baseline curve, which is at room temperature, 25 degrees C. Next curve is the circuit operating at 65 degrees C. And the last curve is the circuit operating at 125 degrees C. Chart on the left, that is microstrip circuits using 5mm RO3003G2 laminate, and it has a very good TCDk. And here you can see at 77 gigahertz, the difference in dielectric constant due to heating from 25C to 125C is 0.01 at 77 gigahertz. So that's a pretty small change. Now, if you look on the right, that chart is using the same circuit, same design, except the material is a 5mm PPE-based material from one of our competitors. And here, the same type of testing across the same temperature range. You can see there's a difference about 3 times that of the RO3003G2 materials, and here we get a dielectric constant difference of 0.031 at 77 gigahertz. Another item to consider is moisture absorption, and a worst case scenario for moisture absorption is a circuit at elevated temperature and high moisture absorption. And the test that we're showing here is based on a conditioning environment of 85-85, and what I mean by that is 85 degrees C, 85% relative humidity. And what we do in this test is we initially condition the circuits per IPC, and then we take a baseline measurement. Then after that, we condition the circuits in the 85-85 environment for 1 day all the way out to 10 days. And each one of these we will take data, and here we're showing the dk versus frequency curves, same as the last graphic actually, but in this case it's showing differences due to being conditioned in the 85C and 85% humidity. Now the material on the left, those circuits were using 5mm RO4830 laminate, and you can see at 77 gigahertz there is a pretty small difference of 10 days conditioning in the 85-85 environment. The dk difference at 77 gigahertz is 0.027, and then on the right, the same testing, same design, same everything, except the circuits are using a different material. This is a 5mm thick competitive material. It's a PPE-based material, and here that same conditioning gives a difference in dielectric constant at 77 gigahertz of 0.062, a little more double than the RO4830 laminate performance. Shown here is a graphic of long-term thermal aging, and what we've done here was actually test the raw materials at several different temperatures over different periods of time, and from that we can get the accelerated aging that we're showing here. Now this is assuming room temperature 25 degrees C over a very long period of time, and you can see that the data with the blue dots are the RO4835 laminate, which is formulated to be very stable for long-term aging. And here you can see a pretty minimal amount of change all the way out to 1 times 10 to the 8th. Now 1 times 10 to the 5 is 11.4 years, so this is a really long time frame here. Now looking at a competitor material, this is also a hydrocarbon laminate similar to RO4835 in some regards, but obviously when it comes to aging and thermal aging, it's not performing quite as well as our material. So the thermal set materials can age differently, and in this case the 4835 is showing a material that's formulated to be optimal with these long-term conditions. In summary, the thermal management is a pretty big topic for understanding reliability and thermal stability. So we talked about that some. Also, other aspects that can impact RF stability and reliability is the TCDk. Now, I did not mention TCDf, which is the dissipation factor temperature coefficient, and also TCIL, and that relates to insertion loss for the thermal coefficient. Now what that means is the insertion loss will change with temperature. Now we do have that data, but I did not have time to go through that here today. And I would invite you to go to our Rogers Technology Support Hub, and after this video you will have a URL that will direct you to that website. Now a couple other things I talked about: moisture absorption, that can be very important to understand for long-term aging and also stability and reliability. And then finally, long-term aging. So long-term aging is also an issue that can cause differences in RF performance. Therefore, the stability may be a little different over a long period of time. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.